So next speaker is Andre, who's going to talk about that.
Right. How does the laser pointer work? Okay. All right. Well, thanks very much, and thanks to the organizers, especially to Joe. So I would like to talk about what? Well, you're one of the organizers. No, you were included, but I think Joe has been working hard on this, hasn't
he? You're rating the organizer.
Huh?
You're rating the organizer.
Okay.
No,
right. So let me talk about heterotic line bundle models. And so this is going to be model building in the context of the fairly established class of Calabi-Yau models. So this is not about introducing a completely new class of string compactifications, but try to push a very well established class as far as possible on the road towards particle physics. Now, it's actually quite difficult in heterotic models to adopt some sort of bottom-up approach to model building. At least I don't know how to do that, because the final information about things like particle spectrum depend in quite complicated ways on the initial geometrical data. So the only practical way to do that, I think at least at the moment, is to scan over a fairly wide range of models and then select within this range of models the one that look reasonable. And that leads you into the realm of algebraic geometry, and because you need to do that for many models, into the realm of computational algebraic geometry. So that gets quite technical, and that's where a lot of the actual work and technical complication of this resides in, and I'm going to cut all that out completely from the talk, because it would get much too technical, and instead just talk about these models from the viewpoint of the four-dimensional effective theories. And so this is mostly about model building, which is related to these two papers with Lara Anderson, James Gray, and Iran Palti. And I'll comment a little bit about modular stabilization, which has been, some mechanisms have been proposed in these papers here with Lara, James, and Bird. And I'll say a little bit how they might apply to these particular models. And I should also refer to some earlier work which contains some of the technical details. Okay, so here's the plan. First, I need to review a little bit these Calabi-Yau constructions. Bert did some of that already, so I'll be brief. Then I'll talk about the structure of these four-dimensional effective theories, explain some general phenomenological issues that arise, and give you an explicit example, then come back to moduli stabilization and conclude. Okay, so what do you need to throw into the game to get yourself one of these compactifications? Well, you need a Calabi-Yau threefold X, of course. You need over it some vector bundle. Bert was talking about the case of a bundle with SU4 structure group. Now you could also consider an SU5 structure group, but I'm not going to do that here. I'm rather considering a bundle with a structure group that is the maximal abelian subgroup of SU5, which is SU1 to the 5. And the corresponding vector bundle will then just be a sum of these 5 line bundles here. And that has a very major advantage, which has to do with the supersymmetry of the bundle, which is very hard to check for non-abelian bundles, as Bert pointed out. But it's rather easy to check here. All you need to check is the vanishing of these slopes, as they're called. The J is the Kähler form. So this is, in fact, just a condition on the Kähler parameters of your model. And then, of course, you need to make sure that the anomaly cancellation condition can be satisfied. So that involves a hidden bundle and possibly 5 branes. We don't construct these things explicitly, but we'll just impose this inequality here, which makes sure that the supersymmetric completion can be obtained. So that's the first step. And when you've completed this step, what you will have is an n equals 4 gut with n equals 1 supersymmetry, and the SU5 gut gauge group, which is the one that commutes with this abelian structure group. But of course, these U1s are also self-commuting. So in addition to the gut group, you get 4 extra U1s. And these U1s, as we'll see, are a bit different from the type of U1 that Bert was talking about. They appear both in the bundle and as the external gauge group, whereas birds only appears as the external gauge group, but not in the bundle. So that makes them different. So you have this extended SU5 gut group, SU5 gut theory with the standard gut multiplets, of course. Then you need to break down further to the standard model, so the typical way to do that is to quotient by a freely acting symmetry. You need to ensure the bundle descends to the quotient space as well, which needs this equivariant condition. Then add on your Wilson line in the hypercharged direction, and that will then break to the standard model group. So SU5 will break into the standard model group, but of course you do retain those 4 U1s, so you get a standard model times 4 U1s. So that's the basic setup. So now, why do we want to do this this abelian business? Why don't we do the normal SUN? Why do we go to line bundles? Well, one reason is that the stability check is much easier. That's an advantage. Another major advantage is that you actually classify line bundles. Line bundles are easily classified by their first Chern class. This is just writing the first Chern class as a linear combination of some basis ji, and these ki's are just integers. So if whenever I say line bundle, just think of a vector of integers. It's very easy, and that specifies the line bundle uniquely. That's not so easy for non-abelian bundles. The further computations that you need to do with the bundles, such as cohomology computations, also get much easier for line bundles. So Bert already explained that you get the number of multiplets here, the gut multiplets as an example, by computing the, say, the first cohomology, if you are interested in the number of 10 multiplets. So H1 of V, that would be the general expression that you need to look at. But in our case, V is the sum of 5 line bundles, so that just breaks up into the sum of these 5 line bundle cohomologies, each of which is much easier to deal with than that of a non-abelian cohomology. And something similar goes for the 5 bar multiplets. And there's another interesting observation here, which is the 10 and 5 bar multiplets, they are not completely structureless anymore. They're not all on the same footing anymore, but it depends on which of these line bundle sectors they actually descend from. So for that reason, I will give them a little index A, which refers back to the line bundle that they're actually coming from. You might be worried about these extra U1s, but that's exactly where this difference comes in. These U1s will normally be Green-Schwarz anomalous, and the vector bosons are very massive, so they're removed. You don't have to worry about them, but they will, the symmetries survive, and they will give you interesting constraints on the 4D theory. Now we will normally be with these abelian bundles at a particular locus in bundle moduli space, which sits in a bigger moduli space, most of which corresponds to abelian bundles. So you might or might not, physically speaking, be at or near this locus. That we don't know, but even if you're not, you might still think of this as a technical tool to explore the wider moduli space at a locus where things become much easier. And indeed, many of the properties of these abelian bundles, they would carry through to the wider moduli space, such as parallel symmetries and so on. But we have to remember that that's the case, and I'll come back to that. Okay, so we have to find some arena where we can do all this explicitly, and that arena is the set of complete intersection Calabi-Yau's, the quintic being the most famous example. But the thing about these spaces really is that you have a classification of them. There are about 8,000 of them, and perhaps even more importantly, you have a classification of the freely acting discrete symmetries. I just checked before the talk. There's actually about 2.5% of these spaces which have freely acting discrete symmetries, which kind of fits with the numbers that we heard earlier, although it's perhaps slightly different symmetries. And thirdly, we can actually compute line bundle cohomology on these spaces. So all the technical ingredients are in place, and I think currently this is the only class of Calabi-Yau manifolds for which that is actually all available. So remember, these line bundle sums were given by integers. So in fact, we have an integer matrix with 5 columns, each corresponding to a line bundle, and the number of rows equals the number of Kähler parameters of the Calabi-Yau. and then we just scan. We pick one of these Calabi-Yaos because the matrix size increases with the number of scalar parameters. We proceed with increasing number of scalar parameters going all the way up to 5, and that amounts to about 60 of these 8,000 spaces. And we also need to place some bounds here, just for practical reasons, on the size of these integers. And if you think about it, if you go to 5 scalar parameters, there'll be 20 integers in that matrix. Each might take about 10 values. So for each of these Calabi-Yaos, you'll be looking at something like 10 to the 20 integer matrices over which you need to scan and sift out the ones that correspond to interesting models. So that even computationally, that's not a completely straightforward problem to deal with. But we've done that, and we find no interesting models on Calabi-Yaos with 1, 2, or 3 scalar parameters, but we do find 2,000 standard models on the cases with 4 and 5 scalar parameters. And there's a green star here, which is there because usually it's at this point in the talk someone asks, what do you mean by a standard model? So I've written this down here, right? So a standard model, by that I mean for this purpose, an n=1 theory with the standard model gauge group times these anomalous U1s and the exact MSSM meta spectrum, one pair of Higgs doublets or possibly more than one pair. We'll see how that comes out. And absolutely no exotics charged under the standard model group. Okay, and so there are 2,000 of these. These models and all the details that we can actually work out, they are available at this database, so you can look at this, and I'll show you an example of the database later. And it's already quite clear that there'll be many more. We have preliminary scans where this number here increases by a factor of 5, but there'll be even more than that. Okay, so let me explain the structure of these models from a 4-dimensional n=1 supergravity point of view. So there'll be many of them. I'll just want to explain what they look like from a 4-dimensional point of view.
2,000 models in equivalent?
There are certain equivalences, and in fact I will come back to that. It depends on what level you're looking at it. So if we, for example, if we identify the models which have the same 4D spectrum, come from the same Calabi-Yao, and have from the same line bundle, then that number reduces to 400. But the ones we have identified, they might still correspond to different discrete symmetries. So they look the same for all purposes that we're currently considering, but they might be distinguished at a finer level. So there are all these, you have to be careful when you give these numbers. They depend on all sorts of considerations like that. So the 4D structure, well, I said the gauge group is the standard model gauge group times these 4 U1s. The charges of these U1s are labeled by 5 integers identified in this way. And then we have 3 families of standard model matter fields, which just for convenience, I group into these SU5 multiples. It's not to say there's an SU5 gut group. It's just for notational ease, and because the U1s here commute with SU5, so every part of these gut multiplets actually has the same U1 charges. There's one pair, or perhaps more than one pair of Higgs doublets, and then there are these singlets here, which are singlets under the standard model group, but can be charged under the U1s, and they, as we'll see, they may be candidates for right-handed neutrinos, although there could be more than 3 of them, but that perhaps doesn't matter. And then the charges are model dependent, but there is a certain pattern which is not, which is always the same. So I've written that down here. EA denotes the 8th 5-dimensional unit vector. So the charges of the 10 multiplets are always such that they have exactly charge 1 under one of the U1s and are neutral under the others. The 5 bars are charged under precisely 2 of the U1s and are neutral under the others, and so on. And this is sort of the same notation as before, right? So a 10 that's charged under the 8th U1 I'll just denote by 10 subscript A, and that of course also means it comes from the 8th line bundle in the higher dimensional picture. Note that these singlets here, while they're standard model singlets, they also all do carry charges under those U1s. That's important for later. So I stress again, there's nothing else here. This is the full matter field spectrum for all 2,000. There are moduli, of course, dilaton, T moduli, complex structure moduli. The first two, they also transform under these U1 symmetries in this nonlinear way, and that's of course part of the Green-Schwarz mechanism and why they are Green-Schwarz anomalous and so on. Should be a bit more precise. I said they are Green-Schwarz anomalous and hence massive almost all the time, but not always. So here is the Stückelberg mass matrix, and it's easy to infer from that the number of masses U1 symmetries is actually easily computed from the rank of this integer matrix. So it's a very, just look at this integer matrix, you'll see. And then we need to discuss supersymmetry. So there's a similar discussion to the one Bert had, but actually all I'm interested in here is the leading term. The other one will be small. So this is the D term. First term is the Filelopoulos term. The second is the matter field term. And we need to set that to 0 for supersymmetry. And the simplest way to do that is, of course, to first switch on all these matter fields. So to be at S equals 0, and try to set the Filelopoulos term to 0 by itself also. If all these remember these matter fields, these matter singlets, they are charged under U1, so if they're all 0, then the 4 extra U1s are unbroken, which means that is the locus that in fact corresponds to the abelian internal structure group that I've been starting with. The other thing you can see, if you want to set these Filelopoulos terms to 0, there'll be a certain bound on the maximal number of linearly independent vectors k, depending of course on the number of scalar parameters. So you get some bound on the rank of this matrix here. And if you put that in, you find that the number of masses U1s is 4 minus the number of scalar parameters. So 5 scalar parameters is the lowest number for which you can avoid massless U1s. And that's why we've gone up to 5 in the scan. Of course, you can do something more complicated. You can try to solve this D term by having the two parts cancel against each other, have some of the S alphas non-zero, because they do carry charges under the U1s. That breaks some of the U1s spontaneously, and that's why we're not really bothered about having some massless U1s after Stückelberg, because we can easily then spontaneously break them. That will reduce these 4 U1s to some smaller number and enhance the internal structure group to a non-abelian group like that. So I can here's a picture just to make that clear. In the first case, where everything is unbroken, all these singlet webs are 0, the Filelopoulos term vanishes. So that forces you in the complex structure moduli space onto some line, this red line here. Yeah, so you're confined. If you switch on small webs, which is something that you can explore within the 4D theory, you'd be able to explore some region, this yellow region here around the line. And then large webs, large singlet webs, is something you would not be able to necessarily control in the 4D theory, so that would correspond to anywhere else here in this moduli space. But as I'll show in a minute, this is in fact something that we can understand by going back to 10 dimensions and constructing the non-abelian bundle explicitly. So let me just give you a very small example of that. Suppose you had some singlet field which carried charges 1 under the 4th and 5th of these U1 symmetries, and you switched on a web for it. Then you'd break the 4 extra U1s to 3 extra U1s, and the structure group would enhance from the abelian one to this non-abelian one, which has this extra U2 factor. And correspondingly, the bundle goes from just the sum of 5 line bundles to, well, the first 3 line bundles stay unchanged, but the last 2, they will recombine into a U2 bundle. And that U2 bundle can in fact then be constructed by this extension sequence here. Yeah? So even if we lose control of the 4D theory, we can still go back, construct the bundle, and then come back down and look at what the theory looks like. So the upshot is that we can explore this full moduli space in that way. Okay, so the ones, while they are Stückelberg broken, they still give you constraints on the theory, and I want to give an example of that. So here I've just written the standard superpotential with the mu term and the up and down Yukawa couplings, and each of these are of course functions of the moduli, which in this case are the singlet waves and the complex structure moduli. So we want to look at this near the abelian locus, so near the locus where S is 0. So we'll just expand those various coupling constants in powers of S. So here's that for the mu term, right? And this constant term here, this S-independent term, that of course has to vanish because we know that we have an exactly massless pair of Higgs doublets at this abelian locus. So this is 0. This leading term here, the next to leading term, linear in S, actually also has to vanish because it turns out that H bar is always neutral under the U1s, and the S's are always charged, so this is forbidden by the symmetries. And then the first term that can arise is this dimension 5 term here, and whether it does or in what pattern it does, of course, depends on your particular U1 charges. So this is constrained by the U1 symmetries. So as you can see, the spectrum that I showed earlier is kind of a generalized NMSSM spectrum, generalized in the sense that there are many singlets. This tells you that the couplings are a bit different. In the NMSSM, you normally want an S-HH bar coupling, a renormalizable coupling. Here, the lowest one is a dimension 5 coupling between the singlets and HH bar. I don't know what that does to phenomenology yet, but it's an interesting difference. So the same goes for the Yukawa coupling. So you write down this expansion, and each of these matrices here will have a particular texture, which is enforced by those U1 symmetries. So you have to then look at the particular model. But just based on this general structure, you can envisage basically two ways of generating fermion masses within those models. So first of all, you do want a large top Yukawa coupling, that's quite clear. And you could do that by asking this Y naught to have a positive rank. Or if that fails, we might get your large Yukawa coupling from one of these higher terms by going to order 1 in these S alphas. Of course, for that, you would have to do what I said earlier. You would have to go back and actually construct the corresponding non-abelian bundle, but that can be done. Now, once you've achieved that, if you still retain some of these S alpha small, so you somehow stay close to the abelian locus, at least in some directions, then you could envisage having some Frogger-Nielsen mechanism. So you have all the ingredients in place. You have not just one U1, but 4 U1s, right? So you can generate the various textures here by having various powers of these singlets as dictated by the U1 symmetries. Or else, if you go away, if you make all these S alphas large, go to some generic place in the moduli space, then you might add some non-perturbative effects to fill out the zeros in the mass matrices. Or in general, of course, you could envisage having a combination of these two as well. The other thing to point out, perhaps, is that even those non-perturbative effects are somewhat constrained by the U1 symmetries in the usual way, so they have this general structure here. And remember that the T's, they contain the T axions, which also had a transformation under the U1 symmetry. So this exponential will transform, and that transformation has to be compensated by whatever matter field terms you have multiplying it. So that's all a matter for looking at detailed models, of course. So now I just want to show you that there is something explicit. This is not just words. There's something explicit actually. So this is one example from the database. So this is one of the 2000. So this is how the output looks like, and this particular page gives you the data that defines the Calabi-Yau for this example. So I don't want to go too much into the details, but that's the integer matrix that defines the Calabi-Yau. It's defined in this particular product of projective spaces. Here's the topological data. So this one has 5 scalar parameters. It has a freely acting Z2 symmetry. And well, here, first of all, this is the volume form. So that's the cubic in those 5 scalar parameters. That's the generator of the Z2 symmetry. So this is one of those things that comes out of Volker Braun's classification of these symmetries. So that's a 10 by 10 matrix which acts on the 10 coordinates of this projective space here. So we know all these things. This is the data that defines the bundle. This is the bundle integer matrix I kept talking about. Don't worry about most of the rest, which is the detailed commodity calculations, but the most important line here is this one, which is the spectrum. And you can see in this particular case, well, we have 3 10s, of course, as we should, but 2 of them have the same charge, the third charge is different, and there's a similar pattern for the 5 bars. We have 1 pair of Higgs doublets, again with a specific charge, and a very specific pattern of singlets with very specific charges, which we can work out and have for all these models. So every one of these 2,000 models comes with the information I'm showing here. So then we can go and we can just classify all these allowed operators allowed by the U1 symmetry. So we can create all these lists of singlet insertions, and here is that list for the Apukaba matrices. So each entry here lists the allowed singlet insertions for that particular entry. If you switch all the S alphas off, then you'll see there are certain ones here. So that will be a matrix of rank 2. So perhaps not ideal, but at least possible to accumulate an order 1 Topukaba coupling. So that would correspond to the first of the 2 possibilities I mentioned to get a large Topukaba coupling. And then you could play your Froggatt-Nielsen by filling in the rest with small singlet wefts, for example. The D Yukawa couplings are completely zero even after singlet insertion. So here you couldn't do a Froggatt-Nielsen. You would have to resort in this particular case, for example, to instantons to fill up the zeros. So then there is the mu term. You see the leading term arises at order 5 as expected. The singlet superpotential would give you, or could give you Majorana masses if you switch on some webs. This term here, again, switching on some webs would give you the corresponding Dirac masses. And of course, all of that depends on the details that you have to look at for a given model, but you have all the ingredients in principle for something like a seesaw mechanism. All these zeros in these 2 lines here tell you that in this particular case, the U1 symmetries forbid all the possibly dangerous proton decay violating operators. So they're all 0. That's not the case for all of them, but in this particular case it is. And here, that's the same game for the Kähler potential, the matter field Kähler terms. The only thing to point out here is that if I set all these s's to 0, you find this texture here, which has to do with 2 of the matter fields having the same charge and the third one having a different charge. If all of them had a different charge, as is the case in some models, then that would be a diagonal matrix, and so that could be quite important if you wanted to avoid flavor changing neutral currents and things like that. Okay, so here's an overview. So this goes from the 2000 to the 400 I was talking about earlier by these identifications. So 400 is the reference number here, and this table is just to indicate how difficult it might be within this set to achieve certain properties. So 230 or so of those have no massless U1 after Stückelberg, 260 with 1 Higgs pair, the other with more than 1 Higgs pair. You get a rank, a non-vanishing order 1 Topukaba coupling at the abelian point in 45 of them. The proton is protected from decay in about 200 of them. And then if you're adventurous and just combine all these properties, you find there's still 13 models left at the end of the day. So this is not meant to be a final statement. It's just some sort of indication how difficult it might be to do things within this class, and it seems possible. Okay, so a few remarks on moduli stabilization. We have the usual, typically large set of moduli, the Dilaton-Kähler moduli, complex structure moduli, and these bundle moduli. And you might first think maybe you want to go along the to-be route of stabilizing these moduli, so to have some Neuve-Schwarz, some form flux added into the picture. That is difficult for 2 reasons. First of all, it's difficult to get W0 small, simply because there are fewer fluxes here. There are Neuve-Schwarz fluxes, but no Ramond-Ramond fluxes, so something like the analog of KKLT would be difficult to achieve because you can't make that small. And then the other reason is that the W0 only depends on the complex structure moduli, not on the dilaton, unlike in 2B, which makes it difficult to realize something like a no-scale scenario. So the analog of the large volume models would for that reason be difficult to achieve here. I'm not saying impossible, but I don't know how. So for this reason, we don't want to do that. I mean, the other reason is, of course, that would get you away from Calabi-Yau, right? That would, then you would lose all your methods. But we don't want to do that anyway. But we will observe that typically we don't saturate the anomaly condition with the observable bundle. So there's a strictly less here. So there is room for a hidden bundle in the hidden E8 sector, and that's another type of flux. So we just want to use that type of flux to fix the moduli. So we already know that putting line bundles can fix some of the Kähler moduli. So that might happen in the observable sector already, but we can also add some in the hidden sector to do that. So that can fix up to all but one of the dilaton and the Kähler moduli. Then Lara on Tuesday talked about how you can use small non-abelian bundles to fix the complex structure moduli, so we can do that as well. We can do all that in the hidden sector. So at this stage we're left with a fairly small number of moduli, at least on the gravitational side, and we're still in a Susy-Minkowski vacuum. And then we can add non-perturbative effects, and we've shown that at least we can then stabilize the remaining S and the remaining T modulus in a Susy ADS vacuum. And of course we need to push that further. We probably need to look at this more carefully and combine all these various effects, possibly in a way similar to what people have done in the heterotic orbifold models. And we hope that this way we can actually get a vacuum with all moduli stabilized and broken Susy. So that would be the idea. We seem to have all the necessary generic ingredients that were successful in the orbifold case. So we hope that can be achieved. Okay, so I'll just conclude. So we can now mass produce these heterotic Calabi-Yau standard models. We've found at this point 2,000 models, but the numbers will keep increasing. They have these additional U1 symmetries, and they're quite helpful. You don't have to actually sit down and compute all these couplings explicitly, at least not at first pass, but they are severely restricted by these U1s. You will eventually be able to calculate some of these couplings. We know in principle how to do it for the superpotential couplings, but the metafield Kähler metric is still a big problem. So that's really an open problem in this context, that there doesn't seem to be even an in-principle method other than numerical to calculate the metafield Kähler metric. So that really has to be resolved at some point. There were a lot of talks about discrete symmetries at this meeting, and we can look at this, and we've in fact started doing this, so we will be able to say something about the possible discrete symmetries. But by this I don't mean the freely acting discrete symmetries I was talking about earlier. They're being divided out. They don't survive as symmetries in the 4D theory, but I mean the ones that would actually be seen in the 4D theory. And I think this is now at a stage where you can really contemplate doing detailed model building, thinking about things like proton stability and fermion masses without setting yourself up for failure. I mean, if you do that in one model, I think you're setting yourself up for failure. I mean, we have many thousands, so I think there's some hope here. And if we can really add moduli stabilization and supersymmetry breaking to this, we can think about the soft breaking parameters, and that would really be where we're heading to. So thanks very much.
So you showed an example with a model where two families had the same charge, the same U1 charge.
Yeah.
So you might think that maybe there's a family symmetry there, a non-abelian family symmetry?
Well, all these U1s are typically family symmetries.
Right, but not the U1. I mean a non-abelian family symmetry interchanging those two families which have the same charge.
That might be the case. It might be discrete symmetry. We haven't yet looked for those, but we will do that. Yeah.
You mean like SU2 or something?
Like E can either be SU2 or a discrete subgroup of SU2.
Yeah, I don't think it will be continuous symmetry. It will be discrete if there's something.
Yeah, but
like
there may be a discrete subgroup
Yeah.
of SU2. So can you just interchange it? Is there an interchange symmetry that you can see interchanging those two families?
I think we have all the tools. I think we can see how to do that, but we haven't done it yet. So.
Right.
If you stabilize with non-perturbative terms and supersymmetry breaking, that would probably stabilize all the moduli. So why are you sort of leaving it to last instead of starting earlier with it?
Because supersymmetry breaking is the most difficult, isn't it?
You have things like ageno condensation that can work.
Yeah, it can work, but you have to make it work.
So.
I mean,
you can
this
sometimes
is
show
not
it.
this is not some sort of generic thing, right? We have a very concrete model with a very specific number of fields, and we have to, it's not just S and T, right? You can't just say, you know, it's e to the minus S, it's e to the plus e to the minus T. It'll work somehow, right? There is that specific number of fields in that given model, which is exactly a standard model, and you have to stabilize all the moduli. You have to explain why you're at this particular point. If you're using a Froggatt-Nielsen, you have to explain why one of the fields is small, and you can use it as a Froggatt-Nielsen field, right? It all comes together. It becomes much more restrictive than the typical generic discussion that you would have carried out 15 years ago.
I'm sort of saying, if you think you need the non-perturbative terms eventually,
Eventually, you do, yeah.
then you would be able to show it's doing all those things for everything if you have to use it. And
Yeah.
you think it might not work or something. I mean,
Well, I don't know yet. I mean, I only know after I've tried, right? We haven't. All I know at this point that we can stabilize all the gravitational moduli in a supersymmetric ADS vacuum. So
okay.
next we have to try if we can actually uplift the ADS and break supersymmetry, and we'll see.
So I actually have a comment and sort of complaint because you quote Stewart's model on the heterotic side, but
Yes.
They didn't actually have any model, so they just did something heterotic.
Oh, well, that's a complaint to Stuart, isn't it?
Heterotic string inspired, but sorry, I haven't done the complaint.
Yeah. All right. Oh God. Now I'm really worried. You know.
No, the complaint is that I with Susha and Saul,
Yeah.
we actually look at the concrete model set 6.2, one of these mini landscape models,
Yeah.
and we actually took everything into account, and
Okay.
we couldn't
Okay, very
find.
good. Yeah. We'll certainly look at that. I mean, this wasn't meant to be a comprehensive list of papers in
yeah,
moduli
there are not
stability.
many. There's only.
Okay.
Let me comment on the comment. So the point that Andre was making is that the particular model that we looked at in our paper has all the degrees of freedom and not more than the ones that he may need
Yeah,
to describe his theory.
heterotic string inspired. That I agree, but it's not more.
But it was a supergravity construction which actually did Susie breaking, stabilized the moduli that we had, and did uplifting to get
Yeah,
this. That's what he's. But it doesn't matter. That's what
No.
he's going to look at because that's very similar to the states that he has in his theory.
Yeah. And I'm sure they'll be very
So it's
similar to the
relevant.
states in your theory. So we'll probably be looking at both.
Okay, so I guess that one carries on over lunch. Tina?
In these geometries you're considering, how hard is it to actually, classify the worldsheet instantons that would give you non-perturbative terms and see, if they cancel and stuff, because you could now really compute it.
Yeah, you can, and that would be the next
Hard,
step.
very hard.
Well, it's as hard as the computations that have been done for some examples, I guess. It's, probably classifying the instantons is not that terribly hard. Computing the prefactors is probably a bit harder. Yeah.
The way with your U1s and the way the charges of your 10s, can you ever get a rank 1 up quark U cover matrix at tree level?
Say that again. What?
The U cover matrix for the up quarks, can that ever be rank 1 without?
Yeah. No. Okay. I didn't say this very clearly. When you are exactly at this split locus, so when the internal group is completely abelian, then the rank of the up U cover matrix is either always 0 or 2 or possibly 3, right? So that's in fact the example I showed you. It was rank 2 in that case. So to do that, you would have to go away and you would have to make the structure group slightly non-abelian. So have a U2 factor in there, as I explained. But we can handle that. And so that would be the second way of that I explained of getting a large top U cover coupling. But that's perfectly possible.
And you said seem to have to expend some effort to remove massless U1s from your theory, but is that, strictly necessary? Sorry, you seem to have you expended some effort in removing all the massless U1s from your theory.
Yes.
But is that strictly necessary? Have you thought of models in which you leave one or more of these in the spectrum?
Yeah, and they exist. I mean, so for 4 Kähler parameters, say, you always have at least one massless U1 after Stückelberg. For 5, generically, in most models, they'll be all Stückelberg heavy, but for specific choices, you'll have one massless one, say, left over, and then whether you choose to spontaneously break that or not, that's a matter of where you are in the moduli space. So yeah, there could well be massless ones left over, but you have to think about what you do with them. I mean, in principle, you could think about similar kind of runnings that Bert Overwood was talking about. But yeah,
Well, there's all sorts of things you can do.
that's not what you meant. Okay, sorry.
He doesn't want me to. That's in private.
You want to ask about the cosmological constant?
Not for your D terms. You can. One possibility will be that all the t's goes to 0. That's not one obvious solution of the D term equation.
Not to 0, no. Oh, sorry. Yeah, I've used a slightly strange basis for the t's. These were the t's with the indices darts. I'm kind of hiding something. Actually, this goes like 1 over t. So the solution would be all the t's go to infinity. So that's the decompactification limit. But just like 1 over s, and it's the weak coupling limit in which it goes to 0. Yeah.
Okay, so any more? Okay, thank you very much.